Can you see my writing now?
Yeah, we can.
So all I wrote before was I wrote down the word product and then equalizer. Yeah, the handwriting seems to be terrible on this board. It's even worse than it would have been. Okay, so, and then we want to get to the notion of limit. And then we said that we go back to motivate this notion maybe from a third example, which is linking it back to the usual limit that we are familiar with on the real line. And specifically, let us consider the sequence 1/2, 1/3, and so on. So the general term of the sequence will be 1/n. And then we know, of course, the limit of this sequence is 0. We can present this limit and each of these numbers as sets. How do we do that? For example, we could take the interval 1 infinity, and then we could take, okay, I think this one should, hello, Danny. Danny is my cat who wants, is requesting some cuddles, but you'll have to wait a little bit, Danny. Okay, so I think what I wanted to say was minus infinity to 1 here. And then we have a subset, minus infinity to 1/2. And that one has a subset, minus infinity to 1/3. And it goes on like that infinitely. So this is how we can think of these numbers as objects living in the category of sets. And then if we apply the idea that we've proposed for product and equalizer to this diagram, so what would that be? We're looking for an object for a set L that has an arrow going into each of the objects in the diagram. And we will call them projections. So this could be P1, this could be P2, P3, and so on. So just to remind you, when we defined the product of two objects, our diagram was such. So we had x, y, and then we had x cross y, and now I'm going to write it at the top to compare it with the other one, with product projections being pi1 and pi2. And when we had an equalizer, the diagram was of the following form. So we had two objects and two arrows, f and g, and the equalizer of f and g was an object with arrows. We actually only had arrow going into x, but that's because the other arrow we get for free by composing that with f or g, which must be equal to each other. So this is the composite f with equalizer of f and g, which equals g composed with the equalizer of f and g. And as you see, these things are equal, and more generally, I would want such triangles to always commute. So what I'm referring to now is, for instance, this triangle. But also all the other ones, also this one, and so on. So P1 should actually be P2 composed with that substitute inclusion, and P2 should be P3 composed with that substitute inclusion, and so on. That comes from, that's something we didn't have the need for in the case of a product, because in the case of a product, our diagram was such that there were no arrows initially given to us. But here, in the case of an equalizer, we had some arrows. And in fact, because of that commutativity of that triangle, that's why we didn't even care of defining the second arrow going into Y, since by commutativity, that second arrow would then be uniquely determined by the first one. But because there are two arrows that are parallel to each other, we want the same triangle. I mean, we want the diagram to commute for the same arrow descending down to Y, and that's what forces those composites to equal each other. Okay, so back to the category of sets where we're now looking for a set L that will have functions P1, P2, P3, and so on to all of these sets that are described below. And it will have the property that, first of all these triangles that are formed commute. In other words, if I introduce some notation now, let's call this I1, and let's call this I2, and so on. And then commutativity of the triangle, of a general triangle, would be that each Pj must equal Ij composed with Pj minus 1. Okay. Okay, so what is the condition that this L together with all the P1, P2, P3, and so on must satisfy? And the condition is that if I have another set M with another similar data of arrows going into each node of this diagram downstairs, let's call them Q1, Q2, Q3, and so on. Again, with all the commutativity requirements, so Qj equals Ij composed with Qj minus 1. So if I have another such M with all the Qs, then there will exist a unique morphism here from M to L. So there will exist unique H such that, so H is unique by the following property. First of all, it's a map from M to L. And secondly, it makes these P's and the Q's compatible with each other. So basically for every I, we want to have that P, or let's say J, because I'm now using I for the arrow. For every J, we want to have Pj composed with H equal Qj. An object L, along with the maps P1 and so on, so it's actually a family of maps, right, indexed by natural numbers, will be then called the limit of this diagram, the diagram that's surrounded with this border here. If it has the property that every M together with a sequence of morphisms Q1 and so on will have a unique H satisfying the stated condition. Does this make sense so far?
Yes.
Mm-hmm. Okay, so Of course, what we want to prove now is that the limit of this diagram is 0. In other words, we actually want to prove that we could choose L to be the set minus infinity 0. And let's just give it a try. We first have to, of course, define what we mean by P1, P2, and P3, and so on. But I guess we could take them to be. Any suggestions? What should we let the arrows P1, P2, and so on be if I want L to be the set minus infinity to 0? What would be a natural map, let's say, from the set minus infinity to 0 to the set minus infinity 1? Any ideas?
Could we have a map that just adds 1?
Okay, we can give that a try. So that would be, so P1 would add 1 and P2 would add half.
Yeah.
So, okay, that's an interesting idea. The problem, though, is that then this triangle will not commute. I first add a half, then I insert it here. It's not going to be the same as adding 1. Do you see that?
Yeah.
Making some space on the board while everyone's still thinking. Any other ideas?
Could you just use a projection map, so take everything and map it to itself?
Yes, we could try to do something similar as we did with the eyes, right? So we could define Pj of a number k or r, let's say, equal r. Just like, remember that that's how i's are defined as well. Ij of r is also equal to r. They're just subset inclusion maps. So let's give that a try. First of all, do we see that the triangles commute? If I take r and I map it by I j minus 1, I'm going to get r. And then, sorry, not ij minus 1, p j minus 1. Pj minus 1. I'm going to get r, right? And then when I map it by ij, so I'm trying to verify this, right? When I'm up by ij, I'm going to get r still. And that's exactly what I'm going to get by mapping r by pj. So it seems like this works, right? Brandon, do you agree with that?
So far.
Okay, now let's prove that. So we get what is called a cone. I didn't say this. Maybe I should have done that. So a cone of the diagram, of this specific diagram, is an object L, together with these sequence of maps descending down to every object of the diagram below, such that each of these triangles commute. In other words, this holds. So L is intended to be a cone, and also M is a cone. And basically, the definition of a limit says that limit is a cone that's universal, in the sense that if you've got another cone, then there is a unique way of connecting them by this H. So we build a cone over our diagram, and now we want to check that this cone is the limiting cone. In other words, that it's the limit of the diagram. So we take any other set M and arbitrary functions Q1, Q2, Q3, and so on. And now we want to prove that when these triangles commute for this other cone, which they must, otherwise we wouldn't call it a cone, then there exists unique H that fulfills this requirement. So we will pick I'm going to write on the left side here, we will pick an element in M, and we will now explore what to do with that X. So H must map it somewhere in L, right? I want to prove that there is H and it's unique. So maybe I can first think of showing that it exists. So if it has to satisfy the requirement written right here, then where would X be allowed to be mapped to? So let's say I map X somewhere here. That spot, whatever that spot is, when I map that further by Pj, right? It should get me to the same place as mapping X directly by Qj. Of course, when I map directly X by Qj, I'm going to get Qj of X. So there's nothing more I know about that, because Qj is some random function. I don't know much about it, so I will just write its value as its value. But does this now help me decide what H should do? Any thoughts on this? So H must map X somewhere in L. So this must be an element of L. And what we know about H is that when we compose it with Pj, it must give me Qj. And so whatever that question mark is, that by Pj must map to Qjx. And remember that M is given to us, and all the Qs are given, right? So for given M and given Qs, I'm looking for the unique H.
Shouldn't it just be Qj of X?
Yep, I agree. This would then have to be Qj of X. There is no other choice, since each of these Pj's will only map Qj of X to Qj of X. It cannot map anything else, because we said already that Pj maps every R to itself. So it seems like there is indeed at most one H. I mean, we are forced to map X to Qj of X, right? But is there at least one? So if we do map X to Qj of X, will that even be a map? The problem with our definition of H, that we are now forced to have H of X equal Qj of X, the problem with this definition is that, first of all, it depends on the parameter J. For which J do we define H of X to be Qj of X? That's the first question to settle. And the second question to settle is whether this value actually lives in L at all or not. Is this actually an element of L? So we've got an element of M, small x, and now each of these Qs are mapping these elements to various elements here, there, and so on, right? What we do know about these Q mappings, all we know about them is that this equality always holds for every J. Qj equals Ij composed with Qj minus 1. Maybe it's actually worthwhile to write this equality out, knowing what Ij does. I see that some things are disappearing on my board, right? I think I had a similar equality here for P. No, this was I. So remember that Ij maps every R to R. So this equality actually tells me that Qj of X will always equal Qj minus 1 of X for every J. So our function is actually well defined in the sense that it doesn't matter what J we put. For two different J's, the answer is the same. So, and that answer is the value of H at X. Okay, so that problem is solved. Now, what about the problem of deciding whether this thing will be an element of L or not? So now we know that all of these Qs are mapping this X to the same spot. So Q1 maps X somewhere in this interval. Q2 maps X in this interval, but Q1 and Q2 map them in the same to the same number, right? So that number, whatever that Qjx is, whatever that Hx is, that Hx is an element of this interval as well as that interval, right? But also it's an element of this interval and so on. Does that imply that H of X will be an element of that interval? So we now know that H of X belongs to all these intervals. In other words, it belongs to their intersection. It belongs to this infinite intersection. What is this infinite intersection? If I take those intervals and intersect them infinitely, what do I get?
The interval from minus infinity to 0.
That's right. So Hx actually does belong to our L. So now, knowing that it was forced to be defined the way we wrote it down, knowing that if we define it like that, then all the necessary triangles commute. It's these triangles. So we define it in such a way that this condition gets fulfilled. Pj composed with H being Qj. knowing that it's so then it has to be defined the way we wrote it down, and then knowing that that value actually is uniquely determined, and knowing that it belongs to L, we've now shown that there is a unique H from M to L, such that for every J, Pj composed with H equals Qj. Does that make sense? So if it's the first time you're seeing this idea, it can be a bit non-straightforward to comprehend because of kind of zoomed out way of thinking about things. We're talking about existence of a unique function and so on and so forth, but there are lots of parameters here, the p's and the q's, and we didn't formally write them out. So it kind of relies on our mind's imagination of what's actually going on here. But I might have lost you throughout the story. So it would be good to give me some feedback where you are, so we can bring you back if you're lost.
I think it mostly makes sense. I'm just trying to like fully comprehend and like wrap my head around it.
Maybe can I kind of make a summary of what we did?
Yeah, I think that would help.
Okay, let me see if I can do a different color here. It seems I can't. Okay. Okay, so we started off with a diagram. It is this diagram right here. And by diagram, I just mean a drawing for now. We will formally define what a diagram is later on. So the objects in this diagram are sets of the form minus infinity to 1 over n. So they're intervals closed on the right-hand side. And there are functions between these sets, and these are just subset inclusions. Every element is mapped to itself in the other set, because every left object is actually a subset of the right-hand side object, right? So we've got this diagram, and we kind of are looking a way to transform this diagram into a single object, which is our L. So that's the idea of a limit. So we want a single set L that interacts with the rest of the diagram through the PI maps, P1, P2, sorry, PJ maps, P3, and so on. Now, this interaction is such that if I transport information from L to this node, let's say, and then I transport further there, I should get the same result as if I had transported directly from L to there. So in other words, we've got these equalities holding. Such a thing is called a cone over our diagram. Now, a cone will be limit when given another cone. So this is now M along with the maps Q1, Q2, Q3, which satisfies a similar equality for every J, which is the one I'm circling now. So given another cone, there must exist a unique H from M to L, which transports nicely. So it's compatible nicely with these projection maps, the P's and the Q's. So if I apply H and then compose that with Pj, that must be the same as Qj. So these are can think of geometrically further triangles commuting. So these kinds of triangles, this one, for instance, and then that one, and that triangle, and so on. So on, it goes on the left side, of course. So that was the problem we wanted to solve. We wanted to find a candidate for L, and the maps P1, P2, all the way up to Pn and further on to infinity, such that for every M and the maps for every maps Q1, Q2, and so on, satisfying the required commutativity of triangles, there will exist a unique H, which again satisfies another requirement on commutativity of triangles. And we've been able to prove that's indeed the case. So we named a specific L, for which we proved that that specific L, together with a specific piece, will be a limit. The piece we chose to be this one's, the one that maps every number to itself. And then we took an arbitrary M, an arbitrary Q1, Q2, Q3, and so on. And then we constructed the unique H. First of all, we can say that we define it like this way, noting that Qj of x doesn't depend on j, since by this requirement right here, Qj of x will always equal Qj minus 1 of x. And so this can go on infinitely. And so by induction, I can show that all the Qj of x's are the same. And so this formula defining h doesn't depend on j. Therefore, it's a valid formula to define a function. But I just have to make sure that this Qj is an element of L, because I'm building a function to L. And I also need to make sure that these triangles commute, these equalities hold. Pj h equals Qj. So these are the two things I need to make sure once I know that h is well defined. Why does Qj of x belong to L? Well, let's call it h of x now. So why does h of x defined that way belong to L? Well, because as we see here, each of these Q's, right, they're mapping this x to these sets, and the value is always the same. So that same value now belongs to each of these sets. So it belongs to their intersection then. And their intersection is, of course, this set. So the first problem is sorted. And then now how do we know that Pj composed with h equals Qj? Well, Pj and Qj, they don't do anything. They just map anything to itself. Sorry, not Qj. Qj maps something to its Qj, but Pj maps anything to itself. Remember, that's how we defined Pj. So then if I map x by h to Qj of x, and then map that by Pj, it will still be Qj of x, and that's exactly what Qj does. So we've shown that we actually do have a map H. Why is it unique? Well, because I want these triangles to commute for every j. In fact, it's enough to have it commuting just for a single j. Then H is forced to be defined that way. X couldn't have gone to any other place, since wherever H would have mapped it to, it must have mapped down to Qj of x, and there's only one thing mapping down to Qj of x, that's Qj of x. That's by the nature of Pj. Pj only maps things to itself. So there can't be another H. It must be this one, if there is one, and we show that this one is the one. And so the proof is done.
Okay, that makes sense. Thank you.
Great. How about others? Brandon, does it make sense to you?
Yes, I'm happy.
Michaela?
I'm happy.
Okay. Okay, so we've now shown a link between the idea of a limit and in a category and the limit of numbers. Of course, this kind of story will only work if we have a decreasing sequence. If a sequence is not decreasing, we might have to use a different kind of diagram downstairs, if we can use one at all. I'm actually not sure about that. I've never tried it out. So if you will try it out and let me know, it'll be nice. But the purpose of limits in a category is not to do analysis in the sense of mathematical analysis, calculus. The purpose is to take limits of mathematical structures, not of numbers. What is fascinating, though, is that we seem to end up doing with mathematical structures similar things to what we've been doing before with numbers. It's a kind of uniformity of mathematics in a sense, and which is exactly what the subject of category theory tries to capture. It tries to understand which aspects of mathematics are uniform across different disciplines. Okay, so now I'm going to show you a different example of a limit. And that one will be called a pullback. It will have various interesting examples still in the category of sets. We're so far, until we get good at limits, we'll be concentrating on the category of sets. So in this case, the diagram will look the following way. So my diagram will now have X, Y, and Z. So this is the diagram. Now think of this as a diagram in the category of sets. And we're now looking for a set L together with the projection functions again. So this will be, I'm going to call this one P1. I'm going to call this P2. And I'm going to call the middle one P3. So you see the picture is similar, except that the diagram has changed. And remember, we have this commutativity requirements, or the triangles. So in this case, there are two of them. So we want F composed with P1 equaling P3, and G composed with P2 also equaling P3. Right? So we have a data of three maps, P1, P2, P3, together with these two equations. But of course, there is a simplification we can do to this data. Knowing that we have P3 that satisfies these two equations, we could just as well say that instead of talking about P3 at all, we could just directly say that F composed with P1 must equal G composed with P2. And once they're equal, P3 can always be produced. It will be whatever they're equal to. And on the other hand, if I have P3, then they will be equal because P3 must equal to both of them. So the notion of a limit can be reduced a little bit. In fact, a cone over such a diagram can be reduced a little bit. I don't have to worry about three maps anymore. I can just worry about two maps with this extra requirement. So I'm going to do that simplification. I'm going to remove P3 and just ask for two maps P1 and P2 such that FP1 equals GP2. Of course, such a diagram would have been called a commutative square if it was a square, but you can imagine we can deform it into one. And now the definition of a limit says that if I have another such, Q1 and Q2, so M together with Q1 and Q2, right? Again, we drop the middle one from M to Z, because if it's a cone over the diagram, then the middle one can be computed in terms of Q1 and Q2 by composing F or G with one or the other. So if there is another cone, then there must exist a unique H. And I don't know if you've seen a user's manual for LaTeX, XY, specifically for a package called XY pick, which is a package for writing arrows in LaTeX. On the cover page, it has exactly this picture. So there must exist unique H such that what? Such that P1 composed with H equals Q1, and P2 composed with H equals Q2. But we should be a bit cautious here. Remember this third arrow that we're kind of ignoring now, we also would have wanted the composites to equal there. So we would have wanted P3 composed with H equaling Q3. But that can be concluded from the other two, because P3 would have been F composed with P1, and P1 composed with H. If that indeed equals Q1, then we get F composed with Q1, right? Which is exactly Q3. And the left side here was exactly P3 composed with H. So we get that P3 composed with H equals Q3. So for the middle arrows, which we removed, a similar requirement would follow from fulfillment of those requirements for P1 and P2. So we can indeed forget about those middle arrows. Just like in the definition of equalizer, which involved a map going into the domain of those two parallel maps, we never spoke of this arrow, because that can be computed again as a composite of the given one with the arrows inside the diagram. So for those who've seen that lecture. Although then we didn't talk about that because we didn't have this general idea of a limit introduced yet. Okay, now our task is to compute what the limit of such a diagram is in the category of sets. So we have two arbitrary sets, x and y, and the third one, z, and two functions, f and g. What should we take as L? What should we make L equal to, so that we get this universal property, that there will be unique H from any other cone into this one? Remember that if there was no f and g, right, we can actually consider a special case of this diagram which kind of makes them disappear. Let's take just for the sake of example, the case where z is a singleton. When z is a singleton, do you agree with me that this condition will always hold? No matter what P1 and P2 we put there, those will be equal. Do we agree on that?
Yes.
Yes.
Sorry, maybe on the side, I want to write a similar equality for the other cone as well. Yeah, so those will be equal because they're maps going into the singleton set, and there's only one element there, so all the values will always be equal. But that means that we can drop this requirement for that case. But then our definition of limit just becomes definition of product, right? That's how we define product of x and y. It's some object with arrows into x and into y, such that for any other object with similar arrows, there is a unique h. So when z is singleton, this L turns out to be the Cartesian product. But what if that is not singleton? What do we do then? So we have to kind of fix up the Cartesian product, right? In a way that would make this work. If I put Cartesian product right here with the general f and g now, with my pi1 and pi2, the problem now is that the diagram no longer commutes. This equality no longer holds. Why not? Well, according to this equality, I should have, if I take pair xy, I map it down by pi1, it will map to x, by pi2, it will map to y, and then f should map x to the same, it's forced to map x to the same spot that g maps y. Fx must equal gy, and this must be true for any pair xy. So it won't work to take L to be x cross y because of this problem. In general, f of x might not equal g of y. But maybe we can actually fix our L in such a way that it will equal. So for which pairs would fx equal gy? It has a very, very simple answer. For which pairs xy is it true that fx equals gy? So what kind of pairs should I put in L so that at least I get the cone condition satisfied? I still will have to establish universal property. If I only had special kinds of xy's, then maybe everything would have been fine. So the answer to the question is very, very trivial. I'm asking for which pairs xy is fx equals gy. Do you want the last chance to offer an answer?
Then we take the x and the y's such that fx equals gy. I mean, if we have
Fantastic,
G already.
yes. Fantastic, thank you very much. Indeed, yes. So the answer to the question is those pairs for which it works, for which fx equals g of y. So we just take those pairs. And notice here that we're actually taking, for those of you who've seen the previous lecture, we're taking the equalizer of the composites f pi1 and g pi2. Do you recognize this this set as the equalizer of f pi1 and g pi2, Michaela? You were there last time.
Yes, I'm happy with that.
But this is just a side remark. If you haven't seen last lecture, don't worry about it too much. You still might want to go back to it at some point, but don't worry about it now. So we take L to be that set, and then we check if it fulfills the requirement of the limit. And remember, there's something we mentioned last time as well. So once we know that something is a limit, we then know all the other limits as well, because something we mentioned last time was that limits are terminal objects in a certain category, specifically the category of cones over my diagram. This condition that for every other cone there is unique h basically tells me that this specific cone is a terminal object in the category of cones. And then we know a general fact that terminal objects, once I know one of them, I know all of them, because all the others will be those that are isomorphic to this one. So once I know a specific limit, all the others will be those that are isomorphic to this one. And the category of sets this reduces to something that's bijective to my set. So up to bijection, we are determining it. And of course, this bijection needs to be compatible with the projection maps. But we'll come back to that a bit later. Okay, so we take this L, and we now want to prove that for every M and every Q1 and Q2, such that this holds, there is a unique H. And let's prove that by similar methodology as last time. We pick an element in X and we try to see, firstly, if we are maybe forced H to be defined in a certain way. So the question is, what is H of X? Well, L is a set of ordered pairs, right? Not all of them, some of them, but the elements of L are ordered pairs, so H of X needs to be an ordered pair. Once I map X here, whatever this H of X is, if I then apply P1 to it, this equation gets invoked. It must be the same.
When
Yes.
you wrote that L is equal to the equalizer of F pi 1 and G pi 2, should those not be P's instead of pi's?
No, these are the pi 1 and pi 2 from the Cartesian product, so from this diagram.
Oh, of course. Sorry, yes. Okay.
But then you're right. So then the P1 then will be the composite of that equalizer with pi 1.
Okay. Yes.
Thanks for that. X is mapping to some H of X, and we know for sure that this H of X by P1, it has to map to the same spot as Q1 maps X, right? It has to map to Q1 of X. But of course, what does P1 do? P1, we didn't say what P1 does. We actually should have done that, right? But it was kind of obvious from our diagram. So P1 is going to take the first projection of the pair, and P2 is going to take the second projection. So it will map X, Y to X, the P1, and P2 will map XY to Y. And that's why Michaela was telling us that maybe these are the projection maps. But remember that L is not the entire Cartesian product, so we can't call it pi 1. P1 is a restriction of that pi 1 onto the subset L. So Q1 of X is actually the first projection of H of X. So H of X is a pair, and its first component is Q1 of X. So I can insert it here. And similarly, on the other side, it must, so P2 must map H of X to the same spot where Q2 maps X, which of course is Q2 of X. And so this one must be Q2 of X. Okay, it seems like, just like before, we are forced for H to be defined this way, but we still have to make sure that this is a valid definition of a function H going from M to L. This time around, there doesn't seem to be any problems with well-definedness, right? There are no other variables here than X. So the right-hand side is uniquely determined by the left-hand side. But the question is whether this belongs to L or not. Remember, L isn't all pairs. There are special ones, the ones where f of x equals g of x. So we'll have to check whether f of this x, sorry, I meant to say g of y the other time, f of x is the same as g of y. That's what we'll have to check, right? F of q1 of x must be the same as g of q2 of x. Carrie, are you fine so far?
Yes.
So why is f q1 of x equal to g q2 of x? We want it to equal, otherwise this element that we are defining hx to be will not be an element of L. Can we guarantee f q1 of x to equal g q2 of x? On the diagram, this would mean that q2 of x, whatever that is, by g will be mapped to the same spot as q1 of x is mapped to by f. So do we have that? Do we know that's true? What do we know about m and q1 and q2? We know it's a cone, right? Does the fact that it's a cone guarantee this?
Yes.
I agree. It's the equality written right here, right? That's so both of them must equal this middle map that we've removed, q3 applied to x. Both of them must be equal to q3 of x. And so they're equal to each other. Okay, so what does that mean? That means that indeed this thing is an element of L. Well, that's good news. So our h of x is indeed a function from m to L. And by the way we define h of x, it's now obvious that these equalities that are required to hold do hold. We defined h in such a way that they will hold. So that part is fine. So we have at least one h. Do we have exactly one h, making those equalities hold? Well, yes, because as we said, these equalities force h to be defined the way we defined it. So there can't be any other way of defining h, not even for any specific element. For every x, it was forced, h of x was forced to be that thing there. So we get that there is a unique h, thus proving that the limit of this special diagram will be the set of xy such that fx equals gy. Should I do a summary on this one as well, or is this one smoother than the other one?
I'm happy with it.
Yeah, me too.
I'm also happy. Can you just remind us again what the diagram is called? Does it have a name? I think it did.
So this specific type of limit is called a pullback. This L, you can imagine this L grabbing x and y, trying to pull it back. So this diagram will be called pullback of fg. So fg is the starting diagram, right? Its limit, together with the initial diagram, is called a pullback, when for any other diagram with the m, there is this unique h. In other words, that the thing is a limit. So this thing is called a pullback. And the dual notion will be called is called a push out. What we do want to do now is to exhibit various different special cases of pullback. It turns out a pullback on its own brings together already several notions, several constructions that are very important in mathematics. We're going to do that in the next slide. So Usually a pullback would be written this way, x cross y with a subscript z, although this notation is a bit ambiguous because the value of the pullback depends not only on z, but also f and g. And if I want to make it a notation that's less ambiguous, then instead of z, I'm going to put the pair fg. So that's another way of writing a pullback. A more precise way, actually, is to put here pair fg. So that's a subscript of cross. And then these ones can be called P1, P2, or Pi1. Sometimes one can also call them Pi1, Pi2. But it's different Pi1, of course, because the domain is now not the entire Cartesian product, but it's a subset of it. So let's remind ourselves what this one was. In the specific case, this one is the set of those ordered pairs xy from x cross y, such that f of x equals g of y. But so will any other set that's bijective to this. If I have a set P that with a bijection B between those things, that will also be a pullback, because then it will give me a cone that's in the category of cones is isomorphic to this one. And so if this one is terminal, the other one will be terminal as well. So we can compute the other projections for this other P by composing P1 with B. So this will be P1 composed with B and P2 composed with B. Remember, the intuition for bijections between sets is that you just rename elements. So when you've got a certain bag of entities, right? Sometimes you don't really care what goes in the bag. All you care is how many there are. And so it's fine if you rename them. If these were called, let's say, X, Y, Z, T, U, you can rename them to A, B, C, D, E. As far as the category of sets is concerned, these two sets are very similar to each other, but we need to keep track of a chosen similarity between them because there are many of them and I don't want to confuse them with each other. So I'll pick one bijection, and once the bijection is fixed, then whatever I can do with one set, I can always do with the other one just by transporting that thing I do with the one set to the other one by the renaming process. And so this idea also applies to limits in general and to the pullback. And we'll actually make use of this idea right now by exhibiting some special cases of pullbacks where instead of presenting the pullback as a subset of x cross y, it will be presented in a different way. But first, let's start with the one that is presented as subset of x cross y. The special case where f is the same map as g. In that case, what do we get? We get two identical maps displayed separately, FF, and then I'll have here X cross FF, P1, P2, and my pullback is then the set of those pairs XX such that, sorry, XY, such that f of x equals f of y. Has anyone seen this construction before? If you've got a function f from x to y, you are sometimes interested to identify all those elements that get mapped to the same spot by f. So every function will partition your set, right? Where things from the same class get mapped to the same spot. If the function is injective, for instance, each of these classes will be just singletons. So then our pullback is nothing other than the equivalence relation that generates this partition. It's called the kernel relation of F and can be written as EQF, equivalence relation for F. In a general category, this is called kernel relation of F. Michaela, have you seen kernel relations before in your work?
Yes.
Great. So that's one case of a pullback when F equals G. Another case is the one we already implicitly considered when Z is a singleton. So in that case, of course, pullback becomes product, Cartesian product. As we already remarked earlier, so I'm not going to spend too much time on that anymore. In the case when when Z is a singleton, and more generally, Z is terminal object. Even in a general category, it actually works. If you take Z to be terminal object, then your pullback will become exactly product. Then the pullback, so then F and G will of course be uniquely determined by the domains, and the pullback just becomes the Cartesian product. Another case, when Y is a subset of Z and G maps every small y to itself. So it's a subset inclusion. So let's figure out what will be pullback in this case. Oops. Just going to move the conclusion for this case. So and the pullback here is the kernel relation of F, which is given by the set of pairs x, y, of x plus x, such that f of x equals f of y. And this is called kernel relation of F. At least category theories, at least some of them, call it kernel relation of F. In the case when y is a subset of Z, so let's redraw the diagram. So now F is any function, F is still any function, sorry, but Y is a subset, and this map here is subset inclusion. So officially, our general formula for the pullback tells us that the pullback must be the set of pairs xy from x cross y, such that f of x equals g of y, but g of y is y, right? So such that f of x equals y. But we can simplify this presentation. So up to bijection. So this is the first time when we're going to replace the pullback we named in the general case with its bijective version. In all the other cases so far, we still wanted to keep the same presentation of the pullback. What is this set bijective to? If you think about this parametrically, so you've got two parameters, x and y, but then you're saying that fx equals y. So you can eliminate the second parameter, right? So I can actually, before eliminating it, let me rewrite this thing. So it can be rewritten as set of pairs x fx, such that x belongs to x, right? Okay, so is it now easy to guess how we can connect this with something that's very familiar to us? Okay, first of all, I lied here, right? This is not quite equal to that. There's a problem. The y must come from capital Y. And by eliminating that parameter, we shouldn't eliminate the condition. So it's the set of pairs fx, x of x, where x is in x, but the y, which is fx, should be in y. So also we should put here that fx must be in y. So it's not all pairs x of x. It's those pairs x of x where fx is in y.
Would this be restricting f to y?
Restricting f to y, yeah, kind of the best way to restrict f to y. So it will be the inverse image of y. And then the P2 map here can be my restriction. And this will be the subset inclusion. So it's all the x's that by fx are mapped to somewhere in y. Of course, this is bijective too. The set of all the to the inverse image of y. In other words, those x's in x such that fx is an element of y. Carrie, are you fine with that?
Yeah.
Great. Last case. In this last case will actually be a subcase of the previous one. This is when f also is a subset inclusion. So just before we move on to that case, the point I wanted to make here is that now we've recovered the notion of inverse image of a subset along a function as a special case of a pullback. So you see how powerful this notion can be. Generalizes simultaneously product, inverse image, and a kernel relation. And there's a fourth thing that it simultaneously also generalizes. Let me try to squeeze that in here. So this fourth case is when f is also subset inclusion. So x is a subset of z, y is a subset of z, and both f and g map every x to itself. Maybe I should talk about y when I talk about the variable under g. There we go. So then the diagram becomes this. And now what will be the inverse? So because it's a special case of the other one, I can just use the computation I already did. What will be the inverse image of y under this subset inclusion function? So those things in here, which by this function map to y. Which subset of x is that? So what goes here? So when x is from x, right, that by this subset inclusion function map inside y. In other words, I want what? So if I look at this definition of inverse image, right? All the x's in x such that fx is in y. Now fx is x, right? So my formula will read x is in x such that x is in y. What is that set? It has a name. So what is the set? What is the familiar name for the set of all the x's in x such that x is in y? Brandon, would you like to help us out?
Intersection.
Thank you very much. I called out on you because you like logic, and intersection is very close to logic. Michaela, does it make sense to you?
Yes, I'm happy.
Carrie, Leanne, are you also happy?
Yeah.
Okay, so there are these four constructions that are captured by pullbacks: the intersection, the inverse image, Cartesian product, and the kernel relation. The last thing I want to tell you about pullbacks is some fun facts, which we will leave as homework for whoever would like to attempt the homework. So, standard facts about pullbacks. If you have a diagram like this, I'm not going to label the objects anymore for this part of the lecture. If you have a diagram like that, that's a pullback. Usually we indicate it by saying PB, the center there. And you've got another one that's a pullback. You can merge these two diagrams by composing the horizontal maps, and it turns out that the resulting diagram will also be a pullback. So we can basically paste pullbacks next to each other. A reverse of this is partially true. So if I've got that the second of these diagrams is a pullback, and the merged one is also a pullback. Sorry. If I know these two facts, then I can conclude that the left-hand side is a pullback as well. And then there are many various fun ways you can combine these two facts with each other. For example, you could consider so of course, all these diagrams are assumed to be commutative. So for instance, when I say here that these two are pullbacks, I'm also assuming that this diagram commutes. In other words, this composite equals that composite. And now I can do something three-dimensional. I could have a cube like this. And let me see if I can get it right. And let's say I know that the back face of the cube and the front face are pullbacks. So sorry, the back, the front, and the bottom are pullbacks. So I know that another way to indicate a pullback is by drawing this little angle thing here. So let me do that. It's easier for the cube. So if this is a pullback, and that is a pullback, and that is a pullback, then it will imply that the top face is a pullback as well. And then there are also other interesting, more complicated consequences of these little facts, which, by the way, are used on kind of daily basis for somebody generalizing various sorts of mathematics where pullbacks come up. Such facts that I'm telling you now are used as steps for calculations. So this implies that this phase is also a pullback. I'm going to leave the other ones as well. And the reason that this is so is that, of course, again, by assumption the diagram is commutative. And the reason for this is that because the back face and the bottom face are pullbacks, then when I merge them, so when I consider this diagonal, this will be a pullback. But this is the same as the diagonal coming from the top face and the front face. And so now I get that the merged one is a pullback. And also the second one is. And then I can apply this fact to conclude that the first one must be a pullback as well. So it's a combination of these two facts, basically. Another important fact is that if I have an arrow F, and it turns out that putting identity maps here, we get a pullback. This is equivalent to F being a monomorphism. And I haven't defined monomorphism yet, but I'm going to do it now. So monomorphism in a category is a generalization of an injective function. In the category of sets, one can confirm this fact by our by what we already remarked, that when I take the same F and pull back along itself, I'm going to get the kernel relation of F. And of course, a function will be injective precisely when, okay, maybe we should go into this bit more detail. So this is the homework to establish these two facts. And now we're going to talk a little bit about monomorphisms. A monomorphism is a generalization of an injective function. What is an injective function? Well, it's a function f such that whenever f of x1 equals f of x2, that implies x1 equals x2. Now, using the language of generalized elements, which was introduced a couple of lectures earlier, we can directly rephrase this definition in the terms of arrows. So I can think of x1 and x2 as arrows having the same source, same domain, going into x. And then if you recall, evaluating a function at an element in the language of generalized elements just corresponds to composition. So now my condition says that for every such diagram of x1 and x2, if f composed with x1 equals f composed with x2, then x1 must equal x2. But then this can be redrawn in a different way. So I've got f, right? Having x1 and x2 with the same source, such that fx1 equals fx2, is the same as having a cone over this diagram of f and f, right? That's exactly what a cone over this diagram would be. Maps x1 and x2 such that fx1 equals fx2. Now, saying that x1 is equal to x2 is equivalent to say that there is a map from C to X, which will be x1 equaling x2, such that composed with the identity map on this left side gives me x1, and composed with the identity map on the right side gives me x1, x2. So existence of, and in fact, uniqueness of H as well. This map will be unique because it's uniquely determined by already x1 because I've got an identity map here. So saying that this H is unique is basically saying that this diagram is a pullback, right? This diagram is a pullback. Is saying that F is a monomorphism. In this specific case, it's the same as saying that x1 equals x2. So we basically proved the last statement from the previous slide, that F is a monomorphism if and only if this thing is a pullback. So once again, what is a monomorphism? It's a morphism F, such that for every morphisms x1 and x2 having the same domain C and having codomain X, if fx1 equals fx2, then x1 equals x2. But this condition can be rephrased as existence of unique H for arbitrary cone over this diagram for the specific limiting cone. So in other words, it can be rephrased as saying that this diagram is a pullback. Is that okay, Michaela? Does that make sense?
Yes, I'm happy.
Mm-hmm. But now, why is a monomorphism in the category of sets the same as an injective function? In the category of sets, we do know that this is the definition of an injective function, but we've adapted this definition slightly here, right? We're now no longer requiring that to hold for the case when C is a singleton. I mean, indeed, when C is a singleton, the definition we have here of monomorphism reduces to the injectivity definition, because a map from a singleton to X is just the same. To name such a map is the same as to name an element of X. The same for the other map. And then these composites being equal to each other, reduced to the values of F being equal to at x1 and at x2. But now we're moving away from singleton to an arbitrary C. Does it still give exactly injective function? Well, I could approach this directly. I could prove directly that this definition gives me equivalent notion to an injective function. So F satisfying this definition are injective function. But I can also make use of my knowledge of pullbacks in the category of sets, because now we're saying that, what are we saying now? Let's move to the new board. So remember that traditionally the way we build pullback, the pullback of F with itself will have a set of pairs xy such that fx equals fy. So this is our kernel relation of F. Now there is another candidate. I'm saying that X with identity maps is also a pullback, and I just need to analyze what that means. if both of them are pullbacks, because each of them is a pullback, the universal property will force this maps going back and forth will actually turn out to be inverses of each other by the fact that two terminal objects are isomorphic to each other. So now I'm basically saying that there is a bijection between this set and X, such that this bijection transports the P1 and P2 maps into the identity maps. So what does that mean? I've got X here, I've got that set. Maybe I'll just draw an element of the set. So I've got XY, right? By the bijection backwards, it maps somewhere, so that then by the identity map, it maps to the same spot as the P1 was mapping this to, which is X. So it must map to X, right? But at the same time, so this is just commutativity of this triangle. But at the same time, we want commutativity of the other one. So it means that also it's true that this one maps by the same bijection, it must map to the same spot where P2 maps that thing to, right? But P2 maps this thing to Y. And so that spot wherever this is mapping to must be, it's the same mapping, so it must be X. But now X by the identity map must map to Y, which means that X must be equal to Y. So what I'm trying to say is that forcing this diagram with identity maps to be pullback is equivalent to saying that this set is given by pairs of the form XX. And remember, this is the equivalence relation that characterizes the partition coming out of F, right? It tells me which things were mapping to the same spot by F. And if each of these are singletons, and that's what this means, right? By the relation, X was only related to itself. So each of these are singletons. That's exactly injectivity of the function, right? I know that I haven't explained this in full detail, and that is part of the homework. I guess just wanted to give you a kind of idea how this links up with injectivity. Okay, now let's say a few words about limits in general. So we have looked at special kinds of limits. We now know about products. We know about equalizers. By the way, the very first limit we considered, this one here, this limit here, that's usually called, I think, would be called directed limit, although directed limit could be a bit more general as well. But I'm not going to mention that now because we only consider it in the special case. And so then we had pullbacks. So what about limits in general? Well, to define a general limit, I need to define a general diagram first, right? So in the case of products, the diagram was over which the limit is defined was a discrete diagram. It only consisted of objects. In the case of equalizers, it consisted of two parallel arrows. And in the case of pullbacks, it had this shape. So how does a general diagram look like? Well, I could say that a general diagram is just a fragment of a category. So there are some objects that we pick and some arrows that we pick. But we actually want to be more general than that. The problem is that if I take the product of x with x, right? What is the limit of this? The limit of xy in general is x cross y. So in this case, the limit will be x cross x, right? But if I don't account for the fact that there are two copies of x, if I replace two copies with just one copy, what is the limit of this diagram? So let's think about it. So it would be some object L with a morphism, right? P. So there's only one projection. No triangles need to be commuted because there are no arrows downstairs. And so the condition is then that for every object M and every arrow Q, there exists unique H. Which L do you think will fulfill this definition? So what do I put here so that for every M and Q, there is always unique H, making the triangle commutative? Lian, do you know what we could put there?
I'm not sure, sir.
Anyone else?
Could it be M itself? No, that
You're close. Because L and P needs to be fixed for all the M's, it can't be M.
so it would be X itself.
That's right, yeah. Indeed, right? So then, of course, H will be unique because by composite with identity it must be equal to Q, then H must be Q, and that's the unique H we can have there. And you see the limit over this discrete diagram consisting of only one object is different from the limit of a similar diagram where now this object is counted twice. So I want in my diagram to take into account how many times the same object will appear. So it's not quite a fragment of a category, right? I can have several copies of the same object displayed several different times. So in my general diagram, objects will be indexed. So I will have dx, I will have dy, I will have dz, I will have dt, where it is possible that dx and dy are equal, but x and y are not equal. This is exactly what's happening here. Here I have d1 and d2. They happen to be equal, but still I want to keep track that they're different. Otherwise, if I don't, then I just end up with limit being just x, not x cross x. So I've got this indexed piece here. And then I've got some arrows. And I could have many or one or several or whatever. There's no limitation on the kind of arrows I can have there. Okay, so first let's define a cone over such a thing. What would be a cone? It would be a single object with a family of maps, one for each index. Remember, this pi1 and pi2 are different maps, even though the x's are the same. Right? Pi1 projects to the first component of the ordered pair, pi2 projects to the second component. They are different maps, but the x's are the same. So even though the indices are the same, the maps might be different. So there is one map for each index. px, py, even if dx, dy are the same, px, py might be different. And so that's my cone, and then it will continue for all the indices. And every time I have a triangle, like the one I've got one here, I've got a few of those. Every time I've got a morphism from dx to dy, this triangle must commute. So going to dx and then composing that with f must equal to directly going from L to dy. So in this specific case now, if these are morphisms f and g, px composed with f as well as composed with g must be equal to py. And if this was morphism r, then r composed with py must equal px, and so on. So this is what a cone is. A cone is a single object with a family of morphisms indexed by the same set as the objects are indexed in the diagram, such that every such triangle commutes. So every triangle that arises in this cone, it literally looks like a cone. So a kind of, not a very smooth one though, it has these sides, which are these triangles. Every such triangle must commute. And then a limit is a universal cone. So a cone such that if I have another cone, so I've got M with a family of morphisms Qx, Qy, and so on for all the indices. There must exist unique H. So for every other cone, there exists unique H, such that each of these triangles commute. So these are the ones that are indexed by a given index. So going from M to L and then going down by P of X for every index X must equal the same value as going directly from M to dy by Qx. So that's how we can formulate the general notion of a limit. And here is a bit more challenging homework. Compute, or rather describe, limits of arbitrary diagrams in the category of sets. We described what products are, what equalizers are, what pullbacks are, but in fact, even for an arbitrary diagram, we can describe what its limit will be. All of these notions, well, first of all, let me remark that this general notion of a limit is indeed general, so it includes all the other three special cases. Let me also remark that the way this is used in mathematics is that very often, very complicated, some mathematical structures are complicated to describe by their elements. The construction is non-trivial. And it helps a lot when you are able to present this complicated construction as a certain kind of limit. Then you just need to know the shape of the diagram, and then you've got the concept. And one example of that is p-adic numbers. I'm saying this specifically because Carey likes number theory. The p-adic numbers can be presented as a limit. I don't remember exactly how now, but we can look at it together at some point. But there are many other constructions also in various areas of mathematics where you've got some complicated object, and you can build it out of simpler ones. And the way you build turns out to be a limit. And since we know general properties of limits and how they behave, and we've got good intuition for them, then knowing the construction reduces just knowing the diagram over which it is a limit, which is much easier to describe than the actual limit. As you will see if you will look at this homework of describing limits in the category of set. So for arbitrary, so you assume you're given arbitrary diagram, and now your task is to write down what L must be. We did that for products, equalizers, and pullbacks, and now it's a task for the general diagram. It's an interesting problem actually to look at. I want to conclude by saying a few words about the dual notion, that of a co-limit. So this is where all the arrows get reversed. The definition of a diagram doesn't change. It's still something that's indexed dx, dy, and a bunch of arrows, any of them. But now a co-limit will have an object C and arrows going up towards C. Again, each such triangle must commute. And the universal property is that if I have another co-cone, this is called a co-cone, right? This time the edge must run the opposite way. So there exists unique edge. And co-limits are also very important constructions. Just to illustrate to you, the dual of pullback is push out, and we can get the Klein bottle, the topological space Klein bottle, very elegantly as a push out of spaces. So remember what a Klein bottle is. It's a bottle that goes back onto here, although it feels as if overlaps itself, but it doesn't. And then, so you pour your wine through this hole. It goes all the way and gets collected here, there. So we can get a Klein bottle as a push out. So I'm going to draw a diagram which now looks outward, right? It will be this shape, and my push out will be given by these two maps. What's the best way to do that? Well, one way we can do that is we take a cylinder. And we take the two circles that we can embed in the cylinder. So this is just isolating this piece of the cylinder and that piece. So now we're working in the category of topological spaces. These are topological spaces. We want to be able to get this topological space up to homeomorphism from simpler spaces. So we take the circle seen as a subspace of R squared twice. So it's actually coproduct of dual of product of circle with itself. And then the circles have orientation, right? Sorry, orientation goes this way. And you want to flip one and match the other one. So you got a single circle here, but these mappings are defined differently for the two. So this one maps directly, let's say, the first one maps directly, and the second one changes the orientation during the mapping. It flips something around. And it flips the direction of going around the circle to the opposite one. So this is one space. This is another one. This is another one. So we get this diagram of wedge-like diagram of topological space, and then we take its push out, and it turns out that its push out is exactly the Klein bottle. And so if I had to write down the formal definition of Klein bottle, I would kind of have to parametrically represent it as a subspace over a four-dimensional space, which will be quite complicated formulas. But as I said earlier, now we can just say that it's a push out of this diagram, a co-limit of this diagram. And to describe this diagram is actually to describe the process of how we build the Klein bottle, right? We take a cylinder and we match its ends in the opposite orientation. That's exactly the intuition of how client bottle is built. And so this example shows you that co-limits, and it also applies to limits, actually capture the intuition of what you want to do with that structure, how you want to get it. And then that intuition is basically captured by describing the diagram. And then the rest is taken care of by general knowledge that co-limits and limits exist in your category. So you prove that once and for all that these limits and co-limits exist in a given category. And then you don't need to construct them every time. You can just describe the diagram of which you want to take limit or co-limit. And it turns out that for what it's worth, things that you want to prove about this constructed object, you will essentially only have to use the fact that it is the limit or co-limit. So you don't almost never have to go back to the element-wise definition of the structure. You can just use its definition as limit or co-limit, which is a considerable simplification to the piece of mathematics you might be working with. Okay, that brings us to the end. And any questions?
None for me. I'm happy.
Yeah, I'm happy as well.
I have a very simple question. What would happen? What would my push out be if instead of this second map that swaps orientation, if it kept the same orientation?
Would it be like a donut?
Yes, it would be a torus. Exactly. Fantastic. Then thanks for joining on Saturday morning, and have a good weekend. We'll talk again next Saturday.
Thank
Thank
you.
you.
Awesome.
Bye.
Thank you, Prof. Bye.
Bye.